Well, this video I made it for you. This is 240 Search a 2D Matrix number 2. Alright, so we're going to write an efficient algorithm. What does that mean? I don't know. Seems kind of self-explanatory considering that we're always trying to write the most efficient algorithm, or we will receive a sorry, you're a great candidate, but we're going forward with other options email. So we're going to write an efficient algorithm. Duh. Of course. That goes without being, that doesn't need to be said. Okay. That searches for a value target in an m by n integer matrix. This matrix has the following properties. Okay. So we're doing some sort of searching algorithm, right? We're searching for a target in a matrix. Okay. Integers in each row are sorted in ascending from left to right. Okay, so it's sorted left to right. So see here, it's steadily non-decreasing, right? So it's 1, everything after that is greater than or equal to 1. 4, 7, 11, 15, right? You can obviously see that this is sorted 2, 5, 8, 12, 19, so on and so forth. And integers in each column are sorted from top to bottom. So it's also increasing, top to bottom, non-decreasing top to bottom. So 1, 2, 3, 10, 18, 4, 5, 6, 13, 21, 7, 8, 9, 14, 23, 11, 12, 16, so on and so forth. Okay. So this problem is pretty simple, right? Like the description is very short, right? It's very intuitive in terms of what they're trying to articulate. And if, for example, if we're looking for the target 5, the target 5 exists in this matrix. If we're looking for the target 20, 20 doesn't exist in this matrix, right? We can literally look at every single value and see that 20 isn't there. For this matrix, well, there's n and m are less than or equal to 300. So technically, this is one of those problems where it's misleading because, since n and m are less than or equal to 300, there's n times m values, right? Because there's n rows and there's m columns. So since there's n times m values and n times m is just 300 times 300 or 9 times 100 times 100 or 9 times 10 to the 4, right? That's definitely doable, right? Often we write algorithms where the limit is kind of like 10 to the 6. So 9 times 10 to the 4 is certainly within the boundaries of what is usually accepted by Leetcode. So that might lead you to believe, oh, well, I'll just do an m by n solution, right? And that's the brute force solution, right? You give me a target, I'll just look through every single row. I'll look through every row and look for that target. If I don't find the target, I'm done, right? But there's technically a more efficient solution. And what should kind of be an indicator that there's a more efficient solution is that, well, this system is sorted, right? So since the system is sorted, that should tell us something about the number we're looking for, right? Like if we're looking for the number 16 and this row starts at 1 and ends at 15, well, we know that 16 is after 15, so it's not going to be within this row. Right? Same with 20. If we were looking for 20, we would know it's not in this row. We would know it's not in this row because it exceeds the value of the largest value in the row, which is to the very right, right? So we know that based on the sorting nature of this problem, sorting the rows and sorting the columns, we can use that information to eliminate some operations, right? But so we got to think about that when we solve this problem. Now, this problem has always been difficult for me, and I just solved it today because this is one of those problems where it's easy to be led down a path that isn't as efficient, right? The clearest path going forward, given maybe your exposure to previous problems, will lead you to do something which kind of leads to a dead end, right? Because when we're thinking of we're looking for a target, right? We're looking for a target in a sorted system. What does that almost always indicate, right? If you've solved other problems like this, if you've studied data structures and algorithms, this is almost always one thing only. And that one thing is binary search, right? It's always binary search. When you see I'm looking for a target in a sorted system, I use binary search. Why? Because with binary search, I can cut the system in half. And since it's sorted, if the value is greater than the value at the half point, then I know it must be to the right. If it's not, I know it's to the left. So now I've taken a system that was full, I cut it in half. Now I look at that half system, I go to the center of that half system. If it's larger, I go to the right. If it's small, I go to the left. Now I got half a half system, so 25%, right? So I went from 100% in one operation to 50% in one operation to 25%. So that's log n time, which is extremely efficient, right? I mean, that's about as good as it gets, right? If you can get it log, besides constant, right? That's about as good as it gets. So we love using binary search solutions. And when we see sorted and we see target, and we're looking for a target in a sorted system, we think binary search almost always. So this is where my brain and most of your brains and probably 80% of the people that initially approach this problem, this is what they thought of first. And this is one of those unfortunate problems where, well, it turns out this, at least for me, didn't lead anywhere good, right? Because how would binary search work in this problem? Well, if we're looking for 5, well, where are we going to binary search first? I guess we could say, all right, well, what does it mean? What does it mean? Because, if we do binary search with respect to rows, right? If we look at this value and we say, okay, it's sorted and I'm looking for 5, well, then I know 5 is to the left, right? But what does that really mean? Well, it means it's not to the right. So it's not this value and it's not this one. And I guess everything below this value is greater than 5, so it wouldn't be any of those values. And since all these values are, boxed in, it would also not be any of these values. So if I did binary search here first, what would that tell me about the system? Well, it wouldn't be any of these values, right? But then where would I binary search next? Okay, well, I could look here and I could say, okay, well, it's greater than 4, so maybe I could box off these values. But then where would I go next? Well, I guess I could, I'm starting to think that maybe there is a binary search way of doing this. If I go here, I can start at 6, and I can say, well, it's less than 6. So it can't be 6 and it can't be anything greater, so it can't be anything to the right. So all these values be blocked off now. Right? Now, the problem here too is how am I deciding what I look at next, right? I made the decision that if it wasn't in a column, I went to the left, right? And then I looked at that column. Or that row or that column or what. So I looked at this column, I said, okay, it's here. So if I looked at this row, well, 3, it's greater than 3. If I'm looking for 5, well, it's greater than 3, so it won't be anything over here. Right, so then maybe my binary search solution would send me over here. So it's the problem with doing binary search in this solution is first thinking about what is that going to do in terms of runtime. I guess I am cutting it in halves every time. But it's also locality issues, right? Because how am I going to decide what I look at next? That's the issue with trying to do binary search here, right? You think binary search, but it's well, after I establish that it's less than 7 here, well, then I know it's not going to be 7, anything below 7, because everything below 7 is greater than 7, and we're looking for 5, which is less than 7, and it's not going to be anything to the right. But then how do I know, where to go next? Because now that I go here, and I say, okay, well, it's not 6, so I know it's not anything below, but how do I know I'm supposed to go left or go above, right? How do I know how to kind of partition this system, cut it up based on things that I know, right? So it kind of takes a solution that really isn't binary search to do this, okay? And I guess the best way to notice it is just to think about, for some arbitrary value, what the implication is when the value is less than or greater than that certain value, okay? So if we're looking for 5 again, right? We're looking for 5, And let's say we just arbitrarily were looking at this 9. Since 5 is less than 9, that means that 5 cannot be in these positions. Why? Because everything to the right of 9 is going to be greater than 5, and everything below 9 is greater than 5. And then kind of like, if you think about that inductively, well then, if what's below me is greater than me, then everything below that is also greater than me. But also, if what's below me is greater than me, and everything to the right of me is greater than me, that also applies to the element below me. So the element below me, everything to its right is also greater than me. So you kind of get this box form here, right? So I know what isn't 9 here. But 9 can still be in this whole system, right? That's what makes this weird, right? Because I can't say like, oh, 5 could be anywhere in here, technically, right? Like if I was looking for 6, for example, right? 6 is in this position here. Oh, excuse me. Let's change that fill to green, right? 5 can be anywhere in here now. So how do we know where to test next? Well, we kind of have like these partition systems. So it's like we can't definitely say, well, 5 is in this system to the left or this system above, right? It could be in any of these systems. It could be over here to the left. It could be kind of diagonally above me or above me here. Okay? But we know for sure that this is the situation, right? If 5 is less than 9, we get this kind of form here where we know kind of everything below us and to our right is not going to be the solution. All right? And that's when we're in particular looking at this 9 value. Right? Okay. All right? And also, let's say we were looking at a different value in a different case, just to kind of make this point as clear as we possibly can. What about when we're looking at me being an idiot? Where do I put these things? I don't know. What about when we're looking at 5 here? Okay, so let's delete this. So let's say we're looking at, Problem is I want a good value. So let's say we're looking for 14. So let's say we're looking at this node and trying to determine what we can eliminate if we're looking for the value, for example, 14. And here's 5. Okay. Well, 14 is greater than 6. So that means that 14 is definitely going to be greater than everything that's below 6. Right? And everything that's to the left of 6. So that means that this whole section is then eliminated. Right? But what that can also mean is that everything else is now a possible candidate. So we kind of know, I guess the general thing here, right, is that it's easy to determine kind of by looking at this, like, what information we can gather in one step, right? From one step, we can figure out exactly what isn't the solution. But then from there, it's not very clear, like, well, what do I look at next, right? To make sure that this is efficient. Because what I don't want to do is, like, keep looking at boxes and then not being able to determine anything about the system from there that doesn't eliminate enough values to get my runtime down, right? Because the whole point of this is to optimize the runtime. So I don't want to like do this process, but I have to pick my next value or the order in which I pick values to check very carefully to ensure that I don't blow up the solution and I look at too many values at once, right? So if we were looking for 14 here, well, 14 could be to the right. It could be up here. It could be to, it could be to the left. It could be any of these values. It could be anywhere in this Minecraft field, right? So I guess what it comes down to is trying to figure out a way that, when we solve this, we can kind of box out the system so there's only one place to go. Okay, and this is probably the hardest part of this problem. So if we look for 5 again, okay, so let's start with a brand new system. and let's look for 5. Always good to start over. So if we start with a brand new system and we're looking for 5, well, one issue with this system here, right, is since we're looking, if we're looking for 14, 14 can be to the right or it can be down. So it's like, do I check 9 next or 13 next? What I should do instead is know which direction I should go based on the value compared to the other value, right? So what I'm basically saying is, from here, the natural places to look next are 9 or 13. But it's hard to pick which one since I'm looking for 14, and these are both greater than 6, right? It could be in either direction. That's the same issue here, right? If I'm looking for 5, well, I know 9 is too big, so I need to go down. But these both go down. So it's hard for me to look at this and say, well, what do I go down to? Which one do I check next? So what if instead we started in a corner like this? If we started here and I'm looking for 5, well, now the directions are more clear, right? If I want to decrease my number, if my number's too big, I go to the left. And if my number's too large, I go down. Meaning if I'm looking for 5 here, right? If I'm looking for 5 in this system and I'm starting here, I don't know if I should look at 8 or 6 next, right? I mean, I guess 6 is closer to 5, but I'm really just thinking about increasing and decreasing. These both decrease. If I'm looking for 5 in here, well, I know, first and foremost, I know that 5 is less than 15, right? 5 is less than 15, so I know that it's not going to be any of these ones here, right? Because everything to the right and down is no longer going to be a solution. And then I only have one place to go, right? The only way I can go is left. I can only go down. I can't go up. I can only go down, right? So I'm going to check this value next. So I'm trying to get this stupid idea. Dumb ideas. So now I'm going to look at this 11 next. And then it's going to be the same exact calculation, right? So I know everything to the right of this is no longer a solution. And I'm going to keep going down. Then I'll look at 7 next. And I'll say, okay, 7 is still greater than 5. So I know this solution is still too big. Then I'll look at 4. Okay, now here's where it kind of gets interesting, right? When I look at 4, what can be said about 4? Well, 5 is greater than 4. So I'm going to go down. I'm not going to go left because I've already kind of gone. If I'm at 4, well, it's greater than me. So it has to be down or to the right, right? Since it's greater than me, well, it doesn't have to be down to the right. It has to be in this system here, right? Since it's greater than 4, it has to be in this system here, right? But since the way I've kind of strategically done this, I've already blocked out everything to my right. The only way I'm over here is if I blocked out everything to the right. So now I know that it can only be in this system here, right? Because it can't be, if it's greater than 4, then it's definitely greater than 4 and everything less than 4, right? So then this system is filled. But since I've already blocked out the systems to my right, I have a closed space that I can check here, right? The issue here is there was no closed space to check first. Do I check 6 next? Do I check 5 next? Do I check 8 next? 12, 19? Here there's an obvious place because I've kind of created this enclosure, right? So now I can check 5 next, and then okay, this is the value that we're looking for and we're good. All right, so let's look for a different value here. Let's say we're looking for 14. Let's say we're looking for 14 in this system, okay? So we'll change this again, just one more example to make this point as clear as we possibly can. So let's look at 14. Okay, so we look at 15. We say 14 is less than 15, so it's definitely not going to be in the system over here. All right. Then we look at 11 and we say 14 is greater than 11. So we don't want to keep going to the left. So it's definitely not 11, and it's not anything less than 11 since it's greater than 11. So then everything here will get blocked out. Whoa. And then there's an obvious next of kin, right? There's an obvious continuation here. Right now we'll look at 12 and we'll say, okay, it's definitely greater than 12. Right? And then we'll look at 16 and we'll say, okay, well, it's less than 16. So that means that everything, why do I keep doing that? Everything to the right here gets changed. So then we look at 9. We say, okay, it's greater than 9. So then everything to the here gets changed. Then we're at 14 and we found our value. Right? And you'll notice that in the system, we only move left and we only move down. So we can only look at mn values, right? In the worst case, I look at all m values and all n, like all, I go m in the, I look at m plus n values in the worst case, right? Because I can only move left and down since I can't move right or up. I'm never going to look at all the values, right? I'm just going to like spiral through the system with at most m plus n moves. Right, you can see that here, since I never go up, right? At any point, I only decide to go this direction or down, right? So since that's the case, we don't have to worry about the fact that, what? We don't have to worry about the fact that, you know, about where we choose our next point, because using the system, we constrain what we look at next. There's an obvious next, because if it's smaller, then we go to the smaller one. If it's larger, we go to the larger one. We always have a smaller and larger option. And then the way that we cut it off, there's a closed system, right? No matter what, there's always this closed system, so we know what to look at next, and we know what values can be next. And we look at most m plus n values. Okay. Now, what would it mean if the value was not in this system? So, for example, let's say the target was 20. If the target was 20, I'm not going to write through the whole system again, but I'll do a new color here. So it's greater than 15. It's greater than 19. It's less than 22. It's greater than 16. It's greater than 17. It's less than 26. It's less than 23. It's greater than 21. It would go here. Right? So it goes most m plus n values. But, you know, if you're greater than this value and you've already gone downwards, right? You were at 23 to get here, and you're greater than 21, well, then your value isn't in the mix, right? Because it's greater than what's above, so it's not above you, right? Because we've already blocked out that system, so then you're out of the game. If you go out of the grid using this system, then there is no solution and you return false. Okay, so with that said, let's go ahead and try to get coding into the solution quickly. Okay, so we'll have our position where we start, right? Our IJ position. So our IJ position is I, well, we start at the 0th row in the jth column, right? At the last column. So that would be I position is 0 and our J position is the length of the matrix at 0. All right. And then what we'll do is we'll just say while true, I guess. I don't know. Or we could say while we're within boundaries. And if we're not within boundaries, return false. So we'll say while we're within the boundaries. So while 0 is less than or equal to I is less than the length of the matrix, because this is our row. So we'll call this row column, actually, just so I don't confuse myself more than I'm already confusing myself right now. The length of the row. So row is less than the length of the matrix. That's the number of rows. And 0 is less than or equal to column, which is less than the length of matrix 0. So this is basically saying while it's in boundary. All right. Now, if our current value at the matrix row column equals our target, then we're done, right? When we ran this, what would happen is, you know, we walked through the solution. If we found the value, we were done, right? We said we didn't find the value, 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 we found 14, we found 14, we're done, right? Otherwise, we say, well, how do we modify this system? If we're looking at the current value, we're looking for 14, or let's look at, damn it. Let's say we're looking for, let's delete all this purple. This is very surgical here. Okay, we're looking for 14 in the system here, right? So we look at, let's say, when we're looking at, okay. We're looking for 14. We looked at 15, and what did we do? We said, okay, the value we're looking for is less than the current value in the system. So let's do that first. So if the value we're looking for, target, is less than the current value that we're looking at in the system, what did that mean to the current row and column that we're looking at? So if the value we want is less than the current value, so that's the case we're looking at right now in our code, we decrement the column, right? We shift the column one to the left. So the row stays the same, but the column gets subtracted by 1. What about in the other case? Else, if the value was larger, right? If the value is larger than the current value in the matrix, we increment the row by 1. We move the row down 1. So then else, so that could be the only case, right? Because either they're equal, it's less, or it's greater, right? We've exhausted all possible things that could happen here. So then we increase the row by 1. And just like that, that's our solution, right? So we only do this as long as we're in boundaries. If we go out of boundaries, that means we've literally tried everything. We got to a point where we couldn't find it, so we're out of the bounds. We started a corner, right? We started a corner because that way, if we start at the top right corner, to our left is things less than us, and below us are things greater than us. So then we always have a direction to go, and then we can always slice out things. And we'll notice using the system, we can only maximize row, right? We can maximize rows for all rows and columns for all columns. So at most, the most values you can do here is row plus columns, right? Maybe I maximize all the row, then I maximize all the columns, but that's how confined the system is. So it's only row plus columns. There's m rows, n columns, n plus n time. I'm saying all this and probably doesn't work, but whatever. Let's run it. Nicely done, Ben. All right. What have I done wrong here? What have I done? So that's the number of rows. That's good. Same row. If target is less than matrix, length of matrix minus 1. Oops. All right, because length of matrix would put you outside of the boundary of the array. You want to start inside the boundary of the array. Embarrassing mistakes made by an embarrassing person. Let's go. Let's go. Okay, so what's the run, space, time, whatever? So for this, it would be, we say n is the number of rows. So that's the length of matrix, aka the number of rows. And m is the length of matrix 0, aka the number of columns. For time, well, like we said, we've already exhausted this point. It's O of n plus m, which is an improvement from the brute force solution, was n times m, right? So we went from kind of this combination, polynomial, whatever, to a linear algorithm, right? So we have to look at all n. At worst case, we look at n rows and then we go down m columns, but it can never be worse than that because the way that we kind of spiral through the system. Okay, for space, well, we just create these two variables and then we just update the variables accordingly. So it's only O of 1 space. All right, everybody, this was a fun problem. Glad I finally solved it. Definitely can be kind of misleading thinking about binary search, but that's kind of how it is sometimes. Peace out.